Okay, I'm going to do a review here of homework two. The first one here, we're talking about when you ignite a piece of paper, why does the paper continue to burn after you've removed the heat source? What's the energy source used for to start with? So I want us to talk about bonds. And so what we should be saying something like the wood is basically glucose, C6H12O6. And and with that, we're using oxygen. And so we're going to break these bonds, and then we're going to form CO2 and H2O, form these bonds. And let's see, this is more energy, less energy. So it takes a limited amount of energy to break the initial bonds, and I get a whole bunch of excess energy back when I form the new carbon dioxide water bonds. So the match is to break the initial bonds that will form CO2 and water. And when that happens, you get heat and light, obviously, but you also use some of that energy to break the next set of bonds with the glucose and the oxygen, perpetuating the cycle until you run out of starting products. So the glucose, most likely, hopefully not the oxygen, although that sometimes does happen. Okay, the next one here. Okay, so on these raised sections, angled sections where the temperature is going up, this is about speed. Why can't it right there? About speed. So this is speeding up molecules, speeding up molecules, speeding up molecules. That's all that's happening in those angled sections. The molecules here are solid, so they're vibrating in place faster. These guys are liquid, so they're moving around inside their container faster, but still in a liquid state. And then these ones are gas, so they're flying around the inside of the container at a faster rate as a gas. Okay, so now what's going on these flat sections? Here, where I don't have any temperature change, but I absolutely have energy going in. That energy is being used to break bonds. More specifically, something called intermolecular forces, which we'll talk about next chapter, I think. So this is also break bonds or intermolecular forces. So there isn't really much to say other than molecules are speeding up on the angled sections. I know that because the temperature is going up, and bonds are being broken on the flat sections. And I know that because the temperature is not going up. So they're not speeding up, they're simply letting go of each other. Okay. All right. So we want to do a heats of formation calculation here. And I wanted you to use this Appendix G. So here's Appendix G. Depending on which book you've got, it's either on 1211 or 1223. And so we would need to go through this and find these different substances and find their values. I'm going to move this out of the way. All right, so this is where we're summing the values before and summing the values after. So it's we use these summations. So summation of all the reactions final minus all the reactions initial. And so what we need to do is let's do the final ones first. So I'm going to go find the values for NO2. All right, so NO2. Scroll, scroll, scroll. Okay, so I'll drag this down here. And so here's the NO2. And let's see, we've got NO2 as a gas. And so NO2 is a gas. Burn it. O2 as a gas. And so the heat of formation is this 81.6. All right, so I'll get that out of the way. All right, so 81.6. Is that positive or negative? Can't remember. It was positive. All right, and this is going to be in kilojoules per mole. But there's two of them. So this is multiplied by 2. And then to that, we're going to add the heat of formation for water. So let's go back up and water as a gas. So heat of formation of water as a gas. So that's negative 241.82, but this is also times 2. And we're going to add those guys together. And then we're going to subtract off what we started with. So then I'll find my hydrazine. Pass it. There's the hydrazine. Got to make sure you get it as a liquid. So that's 50.63. 50.63. Sorry, I should have wrote kilojoules per mole for the other one there. So it's supposed to say kilojoules, joules per mole right there. And let's see, there's nothing. Okay. So it's to the first coefficient, and then we're going to add to the dinitrogen tetraoxide as a gas, and that's 11.1. And then we'll parentheses that. Oh, darn it, kilojoules per mole again there. Sorry, they're all kilojoules per mole. All right, so now let me do the math on this. So it's 2 times 180 or 81.6 plus 2 times negative 241.82. 82. Those parentheses. So that's what we end up with. And so we have to subtract off what we started with, which is 50.63 plus 11.1. Close parentheses equals. And so I get negative 382.1. I don't know why I can't write over there. Sorry. Negative 382.17. Looks like we only have 3 significant figures. So negative 382 kilojoules per mole. That would be our answer for this heat of formation. Okay. And then our last one, we got a Hess's Law problem here. So we got some issues with the stuff that we're given. All right. So I'll start off with that's good. That's good. Those guys are good. Then the N2 is good. That's good because they're in the same equation. The water, too much of that, but it's on the correct side. So I'm guessing we're going to have to flip something. Okay, so those guys are good. We're definitely going to flip this around. And so I'm going to put an arrow here and write H2 plus O2. And then I'll cross off all of this. And then I'll make this negative sign a positive sign. Okay. We're going to have to make it times 2, though. Times 2. And so I'll put a 2 there and a 2 there and a 2 there. Okay. And now I'm good. Now my hydrogen peroxide is correct. State and quantity and side of the equation. And let's see, what else do I need to do? It's like I need to double the middle equation. So you need a different color here. So if I double U and this turns into a 1 and that turns into a 2 and I multiply U by 2 and you're on the correct side. And the reason that all looks good is because there's here's a 4 and here's 2 waters and here's 2 more waters. So my waters are taken care of. And there are 2 oxygens here, one here and one here. Ooh, I need a red's bad. Sorry. Darn it. There we go. I'll choose, I don't know, this guy. So there's an O2, there's an O2, and there are 2 O2s. So these guys get canceled out, which is what we need. And then we have the same situation here, 2 H's and 2 H2s. And so those guys get canceled out. So the only thing that we have left is what we want. We've got this. Oh, that's hard to see. We've got this. That's good. We've got all of those. So that's good. We've got those and we've got this. All right. So then we'll just add all this stuff up correctly. So I've got a negative 622.3. And to that, I'm going to add a negative 285.8 times 2. And to that, I'm going to add 187.8 times 2. Syntax here. Oh, there we go. So I got negative 818.3 kilojoules per mole. All right, that's it. I'll save this and upload it to YouTube.